Our first question, what is PyTorch and how does it differ from TensorFlow? PyTorch is your dynamic AI companion, like having a flexible workshop where you can build and modify neural networks on the fly, while TensorFlow is like a well-planned factory with predetermined blueprints. The key difference is PyTorch uses dynamic computation graphs that build as you go, while TensorFlow traditionally uses static graphs that plan then execute. Think of PyTorch as improvising jazz music versus TensorFlow as playing a classical symphony. Remember, PyTorch equals dynamic and Pythonic, TensorFlow equals static and production-ready. Summary: PyTorch is dynamic, TensorFlow is static for different purposes. Our second question, explain the role of Torch, Tensor. Torch, Tensor is the superhero of PyTorch. It's a multi-dimensional array that can store numbers, perform mathematical operations, and automatically calculate gradients for machine learning. Think of a tensor as a smart container that can hold data in different shapes, like a box for 1 dimension, a table for 2 dimensions, or a cube for 3 dimensions, and it remembers how to do math with itself. Tensors can perform element-wise operations and maintain their computational history for gradient calculation. Remember, tensor equals smart multi-dimensional array with superpowers. Summary: tensors are smart containers for data with mathematical capabilities. Our third question, how do you create a tensor in PyTorch? Creating tensors is like choosing your weapon in an epic battle. PyTorch offers multiple ways to forge your data into powerful tensor form, each method serving different purposes. Just like you can make coffee using instant powder, beans, or capsules, PyTorch gives you various ways to create tensors from different data sources. You can create tensors from Python lists, generate special tensors with zeros, ones, or random values, create range tensors, or make tensors with the same shape as existing ones. Remember, torch.tensor converts data, while torch.zeros, ones, and ran create new tensors. Summary: multiple tensor creation methods serve different data transformation needs. Our fourth question, what is the difference between Torch, Tensor, and torch.tensor? This is the classic uppercase versus lowercase battle. Torch, Tensor is the class constructor like a factory, while torch.tensor is a function like a smart assistant that infers data types automatically. Torch, Tensor is like ordering a large coffee where you specify everything, while torch.tensor is like saying surprise me with coffee where it figures out what you need. The class constructor always creates float32 tensors or uninitialized tensors, while the function infers the appropriate data type from your input data. Remember, tensor gives manual control, tensor provides smart inference. Summary: uppercase gives control, lowercase provides automatic type inference. Our fifth question, how can you convert a NumPy array to a PyTorch tensor and vice versa? Bridge the gap between two AI kingdoms. NumPy and PyTorch speak different languages, but share the same mathematical soul. Converting between them is like being a translator between two powerful allies. It's like converting dollars to euros, same value, different format. NumPy is great for traditional math. PyTorch excels at deep learning. You can use from_numpy to convert NumPy arrays to tensors, or use tensor function to create copies. Converting back uses the NumPy method on tensors. Remember, from_numpy shares memory, while tensor creates a copy. Summary: easy conversion bridges NumPy and PyTorch for seamless workflows. Our sixth question, what are the different tensor data types available in PyTorch? Choose your data type, like choosing the right tool for the job. Each data type has its own superpower. Some save memory, others provide precision, and some enable GPU acceleration. Think of data types like different size containers, a shot glass for small precise amounts, a bucket for large volumes, each serving its purpose perfectly. PyTorch supports integer types like int32 and int64, Boolean types, and floating point types including float16, float32, and float64. Float32 is the default for deep learning, while float16 is memory efficient. Summary: different data types optimize memory usage and computational precision. Our seventh question, how does PyTorch handle device placement? Command your computational army. PyTorch lets you deploy your tensors to different battlefields, CPU for general tasks, GPU for heavy mathematical warfare. It's like choosing between a reliable truck for CPU and a race car for GPU. Your CPU is like a smart chef who can do any task, while your GPU is like 1,000 fast food workers doing simple tasks simultaneously. PyTorch lets you pick the right team for the job by specifying device placement when creating tensors or checking device availability. Remember, same device for operations, CPU tensors with CPU, GPU with GPU. Summary: strategic device placement optimizes computational performance and resource utilization. Our 8th question: how can you move a tensor to GPU? Teleport your data to the GPU dimension. Moving tensors to GPU is like upgrading from a bicycle to a rocket ship. Your computations will blast off at incredible speeds. It's like moving your workshop from your garage to a high-tech factory. Same tools, but now you can build things 100 times faster. You can use the to method to specify CUDA device, or use the CUDA method directly on tensors. You can also move tensors back to CPU when needed. Remember, always move all tensors in an operation to the same device. Summary: GPU migration accelerates computations dramatically for neural network training. Our 9th question: explain broadcasting in PyTorch. Broadcasting is PyTorch's magic trick. It automatically stretches smaller tensors to match larger ones during operations, like a shape-shifting superhero that adapts to fight any opponent. It's like having a smart photocopier that automatically resizes documents to match. A small tensor gets copied to match a bigger tensor's shape for mathematical operations. Broadcasting eliminates manual reshaping by automatically handling dimension compatibility. It works when dimensions are the same size, or when one dimension is size 1. Remember, broadcasting works when dimensions are compatible with same size or 1. Summary: automatic tensor reshaping eliminates manual dimension matching during operations. Our 10th question: what is torch.no_grad used for? Torch.no_grad is your performance booster. It tells PyTorch don't track gradients here, like turning off a security camera when you just want to walk through a room without being recorded. Imagine gradients as breadcrumbs that help you find your way back. During inference or making predictions, you don't need breadcrumbs, so torch.no_grad stops dropping them, saving memory and speeding up computation. This context manager is essential for efficient model evaluation and inference phases. Remember, use no_grad during inference to save memory and speed up computation. Summary: disabling gradient tracking improves inference performance and memory efficiency. Our 11th question: how is PyTorch's dynamic computation graph different from TensorFlow's static one? Dynamic versus static, the ultimate flexibility showdown. PyTorch builds graphs on the fly like improvising a speech, while TensorFlow version 1 writes the entire script before performing. This makes PyTorch perfect for research and experimentation. Dynamic graphs are like GPS navigation that recalculates routes in real time, while static graphs are like printed MapQuest directions from 2005, predetermined and unchangeable. Dynamic graphs provide easy debugging, flexible control flow, intuitive Python coding, and immediate execution. Remember, dynamic equals research-friendly, static equals production-optimized. Summary: dynamic graphs enable flexible experimentation and intuitive development workflows. Our 12th question: what is requires_grad equals true used for? Requires_grad equals true is your learning switch. It tells PyTorch, hey, I want to learn from this tensor, like putting a student badge on data, so the system knows to track how changes affect the final result. It's like putting a GPS tracker on your car. Without it, you can drive but can't track your route. With requires_grad equals true, PyTorch tracks how each operation affects your final result for learning. This enables automatic differentiation and gradient computation for training neural networks. Remember, requires_grad equals true for parameters you want to train. Summary: gradient tracking enables automatic differentiation for neural network learning. Our 13th question: how do you check if a tensor requires gradients? Detective work for gradients. Sometimes you need to inspect your tensors to see if they're ready for learning. It's like checking if your students have their notebooks ready for taking notes. Think of it as checking if your car has GPS enabled. You want to make sure your tensor is set up to track changes, so it can learn from them during training. You can use the requires_grad property to check gradient tracking status. Operations between tensors inherit gradient requirements from participating tensors. Remember, the requires_grad property shows gradient tracking status. Summary: property inspection ensures proper gradient tracking configuration for training. Our 14th question: how do you clone and detach a tensor? Master the art of tensor duplication. Clone creates an identical twin, while detach cuts the umbilical cord to gradients. It's like making a photocopy for clone versus cutting out a newspaper article for detach. Clone is like having identical twins, same data, same properties. Detach is like giving someone independence, same data, but no longer connected to the original's gradient family tree. Clone preserves all tensor properties, including gradient tracking, while detach removes gradient connections. Remember, clone copies everything, detach removes gradients. Summary: clone preserves properties, detach removes gradient tracking connections. Our final question: what's the use of .item in PyTorch? Extract the treasure from the tensor chest. Item converts a single-value tensor into a regular Python number. It's like taking a diamond out of its protective case to examine its true value. It's like removing candy from its wrapper. The tensor wrapper protects the number, but sometimes you need the raw value for printing, logging, or using in regular Python operations. This method only works with tensors containing exactly one element and returns standard Python numeric types. Remember, item only works with single-element tensors for value extraction. Summary: extracts single tensor values for standard Python numeric operations.